Hi everyone, this is Madan Kumar, Assistant Professor, Department of Aeronautical Engineering. In today's class, we are going to discuss about flow visualization techniques, analog methods. Basically, what is meant by analog methods? So it is the method used for solving the fluid flow problems by setting up of an physical system, another physical system. So you need a second domain physical system, and with the help of second domain physical system you are going to visualize or you are going to calculate some of the fluid flow properties. After checking that fluid flow properties, you are going to match it with flow visualization properties, right? So this is basically called as analog methods. So let us see learning outcomes. So these are the learning outcomes. By knowing analog methods, you are going to learn all types of analog methods here. Especially the major 4 analog methods are there according to our curriculum. We are going to see Hele-Shaw apparatus, electrolytic tank, hydraulic analogy, hydraulic jumps, and then limitations of hydraulic analogy, right? So we are going to see all these methods, right? And then you could able to know how these analog methods are functioning, and we are going to predict the authentic mathematical procedure for finding the analogy components with respect to different domains. Let us have some example that if we are going to test any kind of object inside the tunnel, okay, inside the wind tunnel is blown with air. If we are carrying the same model inside a water tunnel, inside the water stream is there, but the properties are different, and with the help of this analogy method, what we are going to do is that we are going to equalize that both wind tunnel properties as well as your tunnel properties, that is water tunnel properties. Okay, that is hydraulic components with respect to water, okay, whichever obtained from the mathematical results, it will be given equivalent to the properties which is measured in the wind tunnel. So this is the equivalent measurement, that is called the equivalent measurement, and then that equivalent measurement is called as analogy. That equivalent measurement is called as analogy. So let me see one. And here this is the working principle. I am going to show the Hele-Shaw apparatus. Here one video is there. Here you are pouring some water and then dye on the other side, right? So this is your rectangular slit where it is operating, right? After pouring, you have to open the opener, which is a valve which is given in the bottom side, and after opening, all the streamlines are coming out from the holes. The gap between the two parallel plates is about 1 mm, and then the diameter of the hole is also 1 mm, right? So the streamlines of water as well as streamlines of dye is coming and it getting impacted on the model which is present in the middle, that is in between the two parallel glass plates, right? This is how the flow simulation is carried out. This kind of apparatus is called as Hele-Shaw apparatus, where all the fluid is coming from one end to other end and it drains into the single pipe, and this pipe we are going to measure the mass flow rate. By knowing the mass flow rate which is coming out of the pipe, we are going to measure the velocity of the flow inside the medium. And this particular Hele-Shaw apparatus is fully suitable for potential flow problems. We are not caring about other kind of problems. It is only suitable for potential flow problem. Potential flow problem means incompressible inviscid flow. So incompressible inviscid flow, for every incompressible inviscid flow, this Hele-Shaw apparatus will be useful for it. Because in this video we can see that we are having the triangular body. If we are going to keep this particular triangle body in a wind tunnel, a large amount of drag will be executed at the adjacent side, right? That is the side which is opposite to the nose corner, right? So we will see that. But here in this section, right, the reattachment zone is very near. So this is the thing, or this is the case that the problem arises. So when we have the reattachment region, okay, it is only occurred in inviscid flow, but it is not occurred in viscous flow, right? So this is a simple inviscid flow which is operating under the Reynolds number of, right, infinite Reynolds number, and it should be kept less than 1. So Reynolds number should be kept less than 1, and it is suitable for low Reynolds number model, and it suits for low Reynolds number model. So we are going to keep this Reynolds number in less than 1, right? And then the other name of flow which occurred here is called as creeping flow, right? So this is called as creeping flow. So let us see one by one how this Hele-Shaw apparatus is functioning, right? Right. Next, we are going to see about the equations evident for Hele-Shaw apparatus or a Hele-Shaw analogy. Right. So, what are the basic equations we are going to take in here? The main important equation considered for Hele-Shaw analogy is that since we are taking the viscous fluid inside the Hele-Shaw apparatus, we are writing equations for Navier-Stokes equation. So, you are writing equations for Navier-Stokes equation, right? So what is your Navier-Stokes equation? Navier-Stokes equation in 3 dimension, it is that u dou u by dou x plus v times dou u by dou y plus w dou u by dou z equal to minus 1 by rho dou p by dou x plus kinematic viscosity times dou square u by dou x square dou square u by dou y square dou square u by dou z square. So this is your x momentum Navier-Stokes equation. I'm going to write the second equation, y momentum equation. So dou v by dou x. It's very simple. When you write the Navier-Stokes equation for x equation, we can simply write, that is, we can change the value of velocity alone, right? I'm just going to change the x velocity component as y velocity component v. It's very simple. And then minus 1 by rho where it is y momentum differentiating with respect to y, and then kinematic viscosity times rho square v by rho x square, rho square v by rho y square, rho square v by rho z square, right? So this is your Navier-Stokes equation, and then you are going to write for z equation, z momentum equation. So it is that u times rho w by rho x plus v times rho w by rho y, w times rho w by rho z minus 1 by rho v by rho z plus nu times rho square w by rho x square, rho square w by rho y square, rho square w by rho z square. So these are the equations that are evident for Hele-Shaw flow. For any kind of viscous fluid which is happening inside the fluid flow, this is the Navier-Stokes equation we are considering at the beginning stage. Here in this axis we are having x and y, which is shown here. It is like x and then y, and then we have the other axis as z, right? So here the z axis is nothing but thickness. So z axis is nothing but thickness. Thickness is nothing but, here we are giving thickness as 2c, right? And this thickness is 1 mm. So here in the video I have been told you about, we have a water tank at the top. This water tank is filled with water on one side and dye on the other side, right? So in between these, okay, we have the slit, and that slit gap is about 1 mm, and then diameter of the hole is also 1 mm, right? And you should know about this, right? It's very important. And then here I am considering x axis, y axis and z axis, where your z axis is nothing but the width, that is distance between two parallel plates, that is 1 mm. 2c is equal to 1 mm. And what happened to the w? W is nothing but z axis velocity. Since your z axis velocity w is equal to 0, and then since there is no flow occurs on the z axis, since there is no flow occurs between the z axis, that is you are considering that the mass flow rate is equal throughout the plate. So since throughout the plate mass flow rate are equal, there is no change in velocity or there is no change in acceleration. So based on that, we are giving the z momentum equation as 0, that is z momentum equation is neglected, right? Just we are neglecting the z momentum equation. So simply I am striking out the z momentum equation, and then the second condition is w is 0, no? So since w is 0, here these terms are going to get cancel up, right? And then since the flow which is happening inside the Hele-Shaw apparatus, so in between the rectangular slits, okay, the flow is fully of viscous force. The flow is due to viscous force only, not inertia force, Since the flow is fully of viscous force, not due to inertia force, that is only with respect to viscous force and gravity force. So with respect to viscous force and gravity force, right? Since it is actuated only with two different kinds of force but not with an inertia force, okay, you are neglecting inertial force. We are going to neglect the inertial force. What are the inertial force? For example, acceleration at x-axis and y-axis, acceleration, and then this with respect to acceleration, second order of acceleration, there is also second order of acceleration are getting cancelled. That is with respect to x domain and with respect to x-axis, where the flow is completely occurring and it's said to be constant, and then with respect to y-axis it is already maintained that the flow rate is maintained constant across the y-axis. So the uniformity of the flow is maintained when the rectangular slits at the top of the tank is getting opened up. All the diameter of the hole inside the water tank, which is found inside the water tank, right, we will have this uniformity of velocity is maintained in x-axis as well as y-axis, so that there is no inertial occurrence in the flow. So when you are going to neglect all these things, so there is no z momentum equation, and then there is no inertial forces, and all the inertial forces are neglected. Only you are going to equate the other x momentum and y momentum equation alone. So what is your x momentum equation and y momentum equation? So let us write. So my x momentum equation is becomes what? In the left hand side all the terms are 0, and in the right hand side we are having the only term minus 1 by rho times dou p by dou x, right, and then plus kinematic viscosity, and then you are having dou square u by dou z square, right, dou square u by dou z square. Since in between two plates, since the fluid is flowing, you are going to maintain the velocity, that is boundary layer growth. So how much will be the boundary layer growth in between the two walls? So that you are considering dou square u by dou z square value, right, and then you have to resimplify this equation as, so bring out this term to the left hand side and write this equation equal to mu times dou square u by dou z square, and then this particular equation becomes as, so mu times dou square u by dou z square. And similarly for y momentum equation becomes dou p by dou y is equal to mu times dou square p by dou z square, right, and here I am writing mu here. So how mu comes? So it is nothing but mu is equal to mu by rho, that is dynamic viscosity by density. So kinematic viscosity is nothing but mu by rho. So by this relation here mu is coming, right. So this will be your equation 1 and equation 2, right. And now you are writing for laminar flow. So for any 2D laminar flow, right. So this laminar flow is nothing but, this is the laminar flow lines, right, all are laminar flow. So all these lines were maintained in a path, and then it starts from top of the tank, and then it ends or it drain up to the end of the opening, right, at the end of the opening. So that for any two-dimensional laminar flow we are writing the equation for u, that is velocity equation. So what is the velocity equation? U is equal to u max times 1 minus z square by c square. You know what is meant by c. C is nothing but 2c. 2c is nothing but distance between the two parallel plates, right, and then again you are rewriting this equation as, so instead of u max you may write the mean velocity. So u mean, so instead of u mean you just write it as um. So u mean 3 by 2 times of u mean 1 minus z square by c square. Similarly you are writing it for v. For u and v you are writing the velocity functions as this. So vm times 1 minus z square by c square. So you have written for u velocity equation and then v velocity equation. Now you have to differentiate this particular equation 2 times. Why? You have to substitute the value and then you have to substitute in equation number 1 and 2. So look at the equation number 1 and 2 and look at the right hand side terms. So we have two right hand side terms, so that you have to differentiate these two components with respect to z 2 times and with respect to z for v also 2 times, right? So on differentiating, right? So first time differentiation, dou u by dou z gives what? So 3 by 2 times um minus 2z by c, and similarly dou square u by dou z square becomes 3 by 2 um minus 2 by c, right? So on differentiating, z square became minus 2z, and then this z is also differentiated to give minus 2, so 2 and 2 are getting cancelled, and then we're writing the equation as minus 3 by c um. So minus 3 by c um is the dou square u by dou z square value. Similarly, we are writing it for dou square v by dou z square as minus 3 by c vm, right? Now you are going to substitute for 1 and 2. So what is your final equation of dou p by dou x? Now you are going to write the final equation for dou p by dou x, and then after that you are going to prove that this particular equation is said to be the equation, that is you are going to prove this particular dou p by dou x and dou p by dou y equation into two-dimensional flow equation, that is two-dimensional irrotational flow equation. By proving it as an two-dimensional irrotational flow equation, you are telling that this particular flow, due to viscous component, you are carrying only the high viscous material, that is dye and water and all, but finally what is the final outcome of the particular view is that the final outcome of the particular view is that it is completely a two-dimensional potential flow, right? That is the main component, that is the thing or case we are going to prove it, right? So in this, so we are having the slits. So this is nothing but the image, a photographic image of this particular tank, right? So which is attached behind the flowing, that is during the flowing times we are having the Hele-Shaw apparatus. So behind the Hele-Shaw apparatus you are just placing some screen, so dark board, and in the dark board you are placing the paper, and then you are taking the photographic image, that is X-ray photographic image, and this is the X-ray photographic image of the particular blood body which is kept inside the Hele-Shaw apparatus, right? So now you are going to substitute this dou square u by dou z square and then dou square v by dou z square value in equation 1 and 2. So finally, what is your equation 1 and 2? So dou p by dou x equal to minus 3 by c square, right? Minus 3 by c square mu um, and then dou p by dou y is nothing but minus 3 by c square mu vm. So this is the equation. Now what you are going to write? Now we have to differentiate this equation 2 and the equation 3 with respect to y and x. So why I am doing is that in order to equalize the terms, so dou square p by dou x dou y is equal to minus 3 by c square mu and then dou um by dou x, and similarly this equation 3 as with respect to x, so minus 3 by c square mu dou vm by dou y or dou x, so it is nothing but dou x. So here it is dou y. You have to differentiate with respect to y and then differentiate with respect to x for equation number 2 and the equation number 3, right? Now we have the left hand side terms. So left hand side terms both are common. So on equality you may write this equation as dou um by dou y is equal to dou vm by dou x, right? And then according to streamline equation we have to mention u. So what is the stream function for u. So u is dou psi by dou y, and then v is minus dou psi by dou x. So this is the stream function. So this is the stream function equation, right? You have to substitute this value instead of em and vm in this particular equilibrium equation. You have to substitute for u. So this becomes as dou square psi by dou y square, and this becomes as minus dou square psi by dou x square. So finally you are getting dou square psi by dou x square plus dou square psi by dou y square is equal to 0. So what is this equation? This equation is nothing but irrotational condition. It is nothing but irrotational condition. So finally the output of the Hele-Shaw apparatus is that even though it is a viscous fluid, but the fluid property behaves analogically. The fluid property behaves analogically as 2D incompressible inviscid flow, and this particular flow is getting into the model, and then this model is having some slit like arrangement. It is also about 1 mm. So in this 1 mm model, the flow is getting deviated from its path. That is, initially we are having detachment and then flow reattachment. That is, upstream we have detachment, and then we have in the downstream we have reattachment. All these things are happening based on inviscid flow problem or ideal fluid flow problem. So this will be purely potential flow. So inviscid flow, so purely potential flow, suitable only for inviscid flow as well as ideal fluid flow. So these are the significances of Hele-Shaw apparatus, right? So let us see the applications of Hele-Shaw apparatus. So applications of Hele-Shaw apparatus. Yeah, here it is there. So here we are carrying a white color dye and then water which is coming up, and it getting mixed up with the model which is kept in between the two rectangular slits, right? This is the circular cylinder. So in this circular cylinder, all the flow is getting attached with the body. So flow in the top side as well as flow in the bottom side. So all the flows are getting mixed up. And similarly in the bottom we are having the airfoil model at 0 degree angle of attack, whether this aerofoil is an unsymmetrical aerofoil. So in this unsymmetrical aerofoil I am going to increase the angle of attack. So when you are going to increase the angle of attack, the flow is getting deviated from its path. So you may see that, and then we will have the boundary layer separation at the trailing edge corner, and also you may see the vortex at the beginning, and then we found the reattachment region very quick. And when I am going to increase the angle of attack in a larger way, so we will have the reattachment point where the boundary separation occurs. So all these kinds of studies can be carried out inside the Hele-Shaw apparatus, right? And then this particular fluid is treated to be as ideal fluid, because after some times all the fluid is getting reattached at the downstream of the subside. Here this demonstrates the source and sink flow. Now I am going to open the source flow. Just when you are going to increase the source flow, all the flow is getting deviated and it resembles the shape of Rankine half body. So it is nothing but Rankine half body. Now you are going to increase the source strength. When you are going to increase the source strength, what happens? The Rankine half body diameter is going to increase. Now I am going to switch it off, right? Now all these streamlines are coming in this way, and now sink is operating. So just I am going to operate the function of sink. So when sink operates, so on the time all the fluid which is coming on the upstream is getting absorbed, and then all the streamlines are looking in the shape of doublet like shape. So it is completely like half doublet like shape. And now I am going to turn on the source flow. Right now I am going to turn on the source flow. When source flow is coming out on the time, and then sink is also operating. So we are having the Rankine wall body in shape, and when we are going to increase the strength, that is source strength as well as sink strength, when you are going to increase the source strength and sink strength, you will obtain the circular shape, that is circular cylinder shape. Right, so these are nothing but potential flows, all are nothing but potential flow models we have been studied in our classes theoretically, but here we can evaluate this particular model practically. So when you are increasing the source strength as well as sink strength, what happens? Your circular cylinder is formed. So finally you are obtaining the circular cylinder. So these are the major applications of Hele-Shaw apparatus, where we could be able to predict all kinds of flow properties in an ideal fluid condition for any arbitrary of bodies. Right? Right. Next we are going to see about electrolytic tank. It's a very simple experiment. Right. This electrolytic tank is nothing but, so here we are carrying the fluid as a water, that is only a tap water, filled with any copper sulfate or aluminum sulfate solution, that is a pinch of solution is there. Right, you are not going to add a large amount of solution into it, so that a tap water with a pinch of copper sulfate is added, and then when it is operating, when the electrode is on, there will be the flow of current from electrode in between the electrodes. So in between positive electrode to negative electrode, there will be the flow of current. So when there is a flow of current, there will be the voltage fluctuation between the electrolyte. Now just we are going to see the electrolytic tank flow separation, which is happening inside the coaxial model. So we are carrying a coaxial model. So we have a hollow cylinder. So in this hollow cylinder, some gap is maintained where the electrolyte bath is maintained. So we are keeping it as electrode. So one is positive electrode and the other one is negative electrode. And let us see this experiment. So for this electrolytic tank, we are carrying three major specific items as an oscillator, and well as step down transformer, and then a null indicator, and then you are carrying the electrolytic bath. Inside the electrolytic bath, you are having a model. Right, so let us see one by one. So in this, so this is the coaxial model. Here this is the probe. This probe is moving, and then right, so from the power supply we are having the oscillator. So this oscillator is connected with the transformer. So this is the step down transformer, and this transformer is giving the output of 50 to 100 volt. So this 50 to 100 volt is attached, right, attached with the two outputs. So these 50 volts are directly given to two electrodes. So one is as plus and the other one is as minus, and then here this neutral point is connected as a probe, and this neutral point is connected as a probe, and this probe is again fitted with this thing, and then here it is the null indicator. So here the value is 0 at the initial case. Here range of voltages are fixed. So for our case it is 50 volt. So since we have attached 50 volt, just we are showing 50 volt, and then here this 50 volt. So here we have several ranges, so 0 to 50, 100, 150, and then 0, 10, 20, 40, 50 as well as, right, when I am switching it on, since the electrode is having the base electrode, it shows 0, and then I am going to turn on the oscillator and setting the voltage as 250 volt. When 250 volt is set, 50 volt will be the output. This will be showing when you are just attaching the probe on the outer ring of the coaxial model. So outer ring of the coaxial model, and then inner ring. Outer ring shows 0, and then inner ring shows the reading of 50 volt. Right? Now what we are going to plot is that, so we have to plot this with the help of the output, that is the probe is getting moving. Parallelly we have to fix a table. So in the table we have a chart. So in this chart we are marking it for different voltage. So what will be the streamlines and potential lines for different voltage. So we have plotted it, and then this is the formula for finding the capacitance, how much the capacitance is there. So epsilon naught epsilon r, so it is nothing but relative permittivity and then permittivity of air, right? And then the delta LT and the delta LN have been calculated, that is change in length, and then after substituting it we are finding this value of capacitance, and then this capacitance is about 32 micro picofarad, right? So 32.88 picofarad is the answer, right? So I think you have understood with the concept. If it is not, let me explain the other. So what are the basic equations evident for electrolytic tank? So for this thing you are considering you are considering the major equation as Laplace equation. So for this we are considering Laplace equation, and you know what is meant by Laplace equation, right? So it is nothing but the equation which satisfies, that is grade square pi is equal to 0. So this is your Laplace equation. So for any kind of electrolytic tank analogy method, we have to maintain the Laplace equation condition, that is irrotationality condition, and as well as potential flow condition, right? And then the flow is completely of two-dimensional flow only, right? So for this you have to write the differential equation for potential lines and streamlines. So what is the total outcome of electrolytic tank is that we could be able to plot streamlines and potential lines. So we can able to plot streamlines and potential lines. For streamlines and potential line we need equations. What is the streamline equation and potential line equation? So for potential line equation, let us consider this graph, right? Here you are considering two potential lines, one is pi and then other is pi plus d pi, and then you are considering 2 points here. So here I am considering 2 points, right? So on these 2 points we are considering two velocities, one is u, here one is v, so it is dx and this is dy, right? So from this equation you may write the equation of potential equation as d pi is equal to u times dx plus v times dy. So this is the differential potential function. This is a differential velocity potential function, right? Which is been right for all kinds of equipotential lines, right? And similarly you should write the equation for streamlines. So equation for streamlines, we are considering two streamlines like this, and then here you are considering 2 points. So here in these 2 points, this is said to be the dx and this is said to be the dy. So here the y velocity is crossing on dx and then x velocity is crossing on dy, that is u, and you are writing equation for t psi. So t psi is equal to here u times dy minus v times dx. So here it is that when the flow is from left to right, it is treated as negative. When the flow is from right to left, it is positive, right? So negative is that from right to left. So when you are sitting here and when you are seeing the flow, it is coming from right hand side to left hand side. So since it is right hand side to left hand side, here I am putting minus sign. But here it is from left to right, here is also from left to right. So when we have any reference plane opposite to that, we have to treat the flow, and then from left to right it is positive, and then from right to left it is negative. So these two are the flow equations considered for potential flow, right? So with these flow equations we could able to plot the value of streamline as well as potential line. So this is the theoretical one. How we have to equate this particular analogy with the electrolytic tank. Now we are considering an electrolytic bath. So inside that electrolytic bath, where the electrodes are kept, in between the electrodes we are keeping the model, right? When the model is when the model is subjected to a voltage of 50 volt to 100 volt, right? And during that time, all the voltages will be flow across the electrolytic bath. So in that electrolytic bath, what happens to the flow? So you are going to measure two types of function. One is electrical potential function and the other is electrical current function. So there are two different kinds of function. Okay, we are going to plot. When you are plotting these two different kinds of electrical potential function as well as electric current function, these two functions are said to be analogy with potential line and a streamline equation. So your potential line equation will be electrical potential equation in electrolytic bath, right? Electrical potential equation, and then the stream function will be the electric current equation, right? Now you have to write the equation for electrolytic tank, right? So for this electrolytic tank, so on the left hand side we are having the figure, just it's showing non-conducting model. So this is said to be a non-conducting model and this is said to be a conducting model, and you know the electrode arrangements. So the electrode are arranged in upstream and downstream of the flow, where the flow is not conducting any current, and then streamlines and potential lines are inversely proposed. And here in conducting model, the streamlines and potential lines are correctly modeled and it is desired. So it is always said to be as a conducting model. Let us see. So this is the arrangement of the experimental setup which have been explained in the video. So where you have the oscillator, and then this is the step down transformer, right? And then we have null indicator, that is a voltage divider, and then from the null indicator you are having from the voltage divider and null indicator we are having the probe, right? And then electrolyte. So this electrolyte is filled with tap water and copper sulfate. Why I am using copper sulfate? Since the model is made up of copper, right? Since here we are going to compute all the electric potential and electric current function, you are going to worry only about the electrical conductivity. So which is going to be the best electrical conductivity of the material. So we are placing copper instead of aluminum. Copper is said to be the best electrical conductivity. So you are keeping copper as a model, right? So this is the experimental setup which I am showing, and then after this, after facing this, what are the primary conditions? That voltage, so voltage given is about 50 to 100 volt, right? And then frequency, that is you are supplying AC current only, AC current of low frequency. So your frequency is about 1000 to 2000 cycles per second. So this is the frequency you are setting down, and then power dissipation. So what is your power dissipation? It should be maintained below 20 to 30 watts. So you should maintain in between this range in order to achieve this current. And then what is your size of the bath? That is electrolytic bath is 2 by 1 meter in size and 10 to 15 centimeter height is maintained, right? And I have been explained that how this particular thing is carried out. Just I am going to move this probe. When you are going to move this probe, this null indicator is getting increased, the value is getting increased, that is voltage across the electrolyte bath is increased, right? So when it is increased, we are getting the voltage variation. The amount of voltage variation around the model is plotted, where you are plotting when the output value is plotted as what? Electrical potential and electric current, right? You have just plotted electrical potential A and then electrical current as B. Let us give this indication, because instead of streamlines and potential lines, we have streamlines as pi and SI, and then but here electric potential as A and electric current as B. So let us write the equation for electric potential. So since you are writing the current intensity formula, just you are writing the current intensity. So what is the current intensity carried between the electrodes? So for this electrodes at any x and y two-dimensional component, so Ix is the current intensity. It is nothing but minus 1 by sigma dou A by dou X. Then Iy is minus 1 by sigma dou A by dou Y. So this is nothing but electric potential function. So A is nothing but electric potential function. So with respect to electric potential function, electric current intensity is written, right? And similarly, current intensities for any kind of electric current. So it is nothing but Iy and Ix. So what is your Iy? Iy is minus 1 by T dou P by dou Y, and this Ix is 1 by T dou P by dou X. What is T? T is nothing but thickness of the model. So here in this model, we are having the thickness. So this is nothing but thickness of the model. So with respect to thickness of the model, we are obtaining two electrical current function. So this electrical current function maps with this electrical current function maps with, right, stream function, right? And these two functions, right, maps with potential function. So this is how we are plotting the potential line and a stream line for any kind of model which is kept inside the electrolytic bath, right? It's very simple, and by using this relation you are writing the differential equation for electrical potential function and then for electric current function. So what is the differential equation? So let us write the differential equation as dA is equal to minus sigma Ix dx plus Iy dy, and then Tb is nothing but minus T Ix dy minus Iy dx, right? So this resembles the equation d pi is equal to what? What is your d pi? U dx plus v dy. And what is d psi? Right? What is your d psi? D psi is u dy minus v dx, right? So these two equations are said to be ideal and it is said to be equal. right? Now with the help of this probe movement, we could able to plot all the results of potential function as well as stream function. So finally, you know what is the output of stream function as well as potential function. At the beginning I have shown you, right? Is there any doubts regarding this? You can post it in the chat box, right? And then next we are going for hydraulic analogy, right? So this is a simple hydraulic analogy, and first of all you should know what is meant by hydraulic analogy. So we have the wind tunnel, so inside the wind tunnel we are getting the results, and now you are going to, instead of running the wind tunnel, since for high speed flow we are going for large ducts and fans, and then you are going to operate it for a long time, and then we need a large storage tanks for running the high speed flows. So there are various disadvantages in high speed flows, but this particular hydraulic analogy will be useful for having the simple model in a simple manner. I can keep that particular model, a small miniature model, in a water flow tunnel, and we may simulate it, and then we may compare it with the real model. So for this we are using this hydraulic analogy. So the analogic method, which is used for qualitative and quantitative study of high speed flows or any kind of high speed flows, this particular hydraulic analogy is important. And also we can go for shallow water flow. So shallow water flow, especially for low speed flow, it is suitable. So let us see the low speed flow model of simulation in a water flow tunnel, which is present in NASA, right? Let us view this video. So here we are having the free surface plate. Above that we are keeping the model, automobile model, and then all the dies are streamlined in a path where the flow behind the model, that is the flow behind the model, is turbulent. So we will see the turbulence of vortices. So we have the flow separation immediately behind the model, and all the vortices are mixed, and then all the vortices are going along the path. Here the flow speed is maintained 10 cm per second. The flow speed is maintained 10 cm per second for the particular model. And then for any kind of hydraulic analogy, we are carrying it with surface free measurement, and then you have to consider the hydraulic depth. Hydraulic depth is nothing but the depth which is considered for initial as well as final. So initially we are having the depth as an initial measurement, as a minimal measurement, and then when the fluid is running, so on the time the depth of the surface water is increasing, and the depth of the surface water is increasing, the change in depth is considered for mass flow rate as well as movement of the fluid variation. So in all the cases we are seeing about, in previous case also we have seen about mass flow rate, that is continuity equation as well as momentum equation. We haven't seen continuity equation, since for Hele-Shaw apparatus continuity equation is constant. Since it is maintained constant, it is left. We are considering only for Navier-Stokes equation. Similarly for electrolytic tank, we are considering only for potential flow. So we are just plotting the potential line and the stream line for any kind of arbitrary models, right? But here in hydraulic analogy, what we are going to discuss is that this hydraulic analogy, right, only these high speed flow models. So we are going to see only the high speed flow models. So what are the high speed flow models which are considered? So what are the major applications also? Application is that transionic unsteady flow past wings, and then transient phenomenon in high speed flows, and then shockwave interaction. In all these cases hydraulic analogy will be there. So we have to use the theory of analogy. So what is the basic theory of analogy? So it is that depth of the flow. So I have been reminding you that depth of the flow is small. Okay, compared to surface wavelength, right? So we are having the surface wavelength, so depth of the flow is small compared to surface wavelength. So it is nothing but if you are considering a bath, right, this is the bath. So here free surface is there, right? So this is the depth, and then this is the length, surface wavelength. So now you are considering the length and as well as depth. So what happens to your physical domain? In your physical domain, h should be smaller than l. So this is the theory of analogy considered for hydraulic analogy, and then governing equations, and then we are also considering governing equations. So governing equations is governing equations in shallow water. So governing equations in shallow water is analogy with, so governing equations in shallow water is analogy with which governing equations? Governing equations of perfect gas, right? So these should be equal. So this is the theory of analogy we should consider. So by considering this theory of analogy, right, first we are going to write it for shallow water flow theory, and then we are going to, after solving the shallow water flow theory, we are going to compare this shallow water flow theory with gas flow equations. So after writing a shallow water equation and gas flow equations, we are going to write the similarity studies, and after writing the similarity studies, and then we are going to write it for non-dimensional numbers, that is Mach number and Froude number, and then after writing Mach number and Froude number, we are going to write about or talk about vorticity, and then what are the depth measuring devices used for hydraulic analogy is also considered here, right? First we are going to write it for shallow water flow model. So for any shallow water flow model, what is the continuity equation, and then what is the momentum equation? Let us write. Continuity equation is dou h by dou t plus dou by dou x hu dou by dou y hv is equal to 0. Then what is your momentum equation? Dou u by dou t, u into dou u by dou x, e into dou u by dou y is equal to minus g by 2 1 by h, differentiation of h square, sorry, not differentiation, dou by dou x. So dou by dou x h square, right? So this is your x momentum equation, and then your y momentum equation is dou v by dou t plus v into dou v by dou x, sorry, it's u, and then v into dou v by dou y minus g by 2 1 by h dou h square by dou y. So these two are the momentum equation, x momentum equation and y momentum equation. And after writing this x and y momentum equation, you are going to resolve the for fixed pressure and fixed density. Now we are going to find it for fixed pressure and fixed density. So it is nothing but fixed pressure. So what is your fixed pressure? It is nothing but Pf is equal to integral over 0 to h. So across the bath, across the surface depth. So across the surface depth, what will be the pressure acting on the surface? So it is nothing but fixed pressure. So it is P into dz, right? So here, what is your P? The P is rho g z, right? Rho g z into dz, and then this rho is nothing but water. In shallow, in shallow, this is your shallow water flow equation, and you are keeping the water as this equation, so that finally after integrating this step we are obtaining the value as rho wg h square by 2, right? And then from this you can write the value of h square as 2 pf divided by rho wg, right? 2 pf divided by rho wg. So this is your h square equation, right? And then we are going to write for frictious density. So what is your frictious density? So your frictious density is that is rho f. And again you have to write it for rho f, so that you are again considering the same frictious pressure equation, rho wg h square by 2. Here frictious pressure is that this frictious pressure is nothing but frictious density times g times and then depth. Your depth is h by 2 is equal to rho wg and h square by 2. So your h 2 is getting cancelled and g is also cancelled, so that rho f is equal to rho w h, that is rho f by rho w is equal to h. Right, now we are going to use this equation, and we are going to transform this particular equation, that is in shallow water flow model you are going to convert this or substitute this value of h. So instead of h you are going to substitute a value in continuity momentum equation, and then we are going to use this h square equation in this momentum equation, and finally you are solving it, and then you are writing the answer, right? So what is your shallow water equation now, right? So after substituting the value of h in continuity equation, right? So this is your continuity equation. So in this continuity equation it is rho by dou t, rho f by rho w. Since your h is rho f by rho w, just you are writing it. So rho f by rho f, it is not rho f. So rho f by rho w plus dou by dou y rho f by rho w v, right, equal to 0. So finally your continuity equation becomes dou rho f by dou t, rho by dou x rho f u plus dou by dou y rho f v is equal to 0, right? Now we are going to write momentum equation. So in momentum equation let us write the x momentum right hand side alone. So we have left hand side, that is dou u by dou t up to left hand side, and then we have the right hand side portion. Similarly we are considering only the right hand side portion. So in this right hand side portion it becomes as, so after substituting all the values of v square, right, after substituting the value of v square it becomes as minus 1 by rho f dou pf by dou y. Here is also minus 1 by rho f dou pf by, sorry, it's dou x and then dou pf by dou y. So this is how x momentum and y momentum right hand side will be changed, right? And then we know the gas equation. So what is the continuity equation for gas? The same thing, dou by dou t of, right, their density is rho g, right, plus dou by dou x of rho g u, dou by dou y of rho g v equal to 0. Similarly we are writing it for momentum equation. It is also dou u by dou t u into dou u by dou x v into dou u by dou y minus 1 by rho g dou p by dou x. Similarly, the same thing, dou v by dou t and y components minus 1 by rho g dou p by dou y. So this is the similarity. So we have the similarity of equation for gas equation, momentum equation, as well as the shallow water equation. So both are said to be equal. Both are said to be equal or similar with each other. Either the value of rho f is maximum than the value of rho g, since density of gas or gas is a lightweight substance here said to be as it is, right? But the similarity is same, and then the flow conditions, flow analogy parameters is also mathematically taken, and we can solve the equations in the same way. And then the readings are different. The readings are different, but with respect to similarity, with respect to flow similarity studies, we could able to solve this particular equation, and we could able to solve all the flow properties around the any kind of fluid domain which is kept inside the hydraulic analogy as well as shallow water model. So what are the similarity studies we have considered for this shallow water flow model as well as gas model, right? So what are the similarity flow models we have considered? Let us see. So here for similarity studies, our first approximation, what is your first approximation? It is that PF. So your PF, right? So this PF is nothing but rho W G by 2 H square. So this is your frictious pressure. So in this frictious pressure, what you are going to do, you are going to substitute the value of H. So you know what is H. So G by 2 rho F square by rho W square. So rho W one time getting cancelled, and it is PF by rho F square is equal to G by 2 rho W, which is nothing but constant, right? So from this equation, what you predict that the value of gamma, it is nothing but this particular value. For shallow water, it is maintained n is equal to 2 for polytropic process. For any polytropic process of water, right, the value of n is maintained as 2. But for gas, right, but for gas, it is gamma is equal to 1 to 1.67. So we are maintaining with a range of 1 to 1.61, but it is n is equal to 2. So for any kind of hydraulic analogy, you are treating the value of gamma as 2, right? So this is the case, important case for similarity studies. And then for the similarity study, okay, you are again treating this value of PF. So what is therefore your PF is nothing but pressure at gas, which is proportional to H square, and then rho F is equal to rho G, that is density of gas, is always proportional to H. So therefore, what is the value of P by P naught? So P by P naught of any model which is kept inside the analogy is H square by H naught square. So during stagnation, so without running the surface water, what is the depth? After running, what is the depth? So H by H naught square. So P by P naught. So this is your stagnation pressure equation with a measured with respect to hydraulic analogy. And similarly, we can write it for density. So rho by rho naught is also H by H naught. Since rho is directly proportional to H, it is rho naught. And similarly, T by T naught. Since P is equal to rho RT, we can also write it for T by T naught as H by H naught, right? And then we can also write it for A, right? That is speed. So what is for sound speed? So your sound speed A is nothing but gamma P by rho 1 by 2. But here for shallow water, AW is there, and then gamma. You know gamma is 2 here, and then PW, right? So what is your PF? So here it is PW and the PF both are same. So it is rho W G by 2 H square. that is PF, and then you are substituting rho F. So rho F is rho W into H, power of 1 by 2. So H and H is getting cancelled, and then rho W is getting cancelled, 2 and 2 is getting cancelled, and finally we are having GH power of 1 by 2, that is AW is equal to root of GH, right? And you may write Mach number. What is your Mach number? V by E, that is speed of gas by speed of sound, right? So that is your Mach number. And then for any hydraulic analogy you are writing Froude number. So this is nothing but Froude number, right? So FR, so it is nothing but velocity of water divided by root of GH, right? So velocity of water divided by root of GH. And then for writing Mach number, m less than 1, m is equal to 1, m greater than 1 is subsonic, sonic, and then supersonic. And for this Froude number, less than 1, equal to 1, greater than 1. So it is nothing but subcritical flow, critical flow, supercritical flow. So the subcritical flow is used for surface water waves, that is surface free waves, okay, that is for subsonic problems. And for critical problem, only transonic flow problems as the study, so that we are going for transonic flow problems for critical case. And then for supercritical waves, so you are considering for shock waves. So for supercritical conditions we are using shock waves. So your hydraulic analogy will becoming as hydraulic jump. So for a hydraulic analogy and a hydraulic jump we will see next. And then we are also worrying about the factor called vorticity. So what about the vorticity occurs? How much amount the vorticity will occur? Let us see. So in this vorticity, right, you are writing curl of V equal to K times rho V by rho X minus rho U by rho Y. So this is for vorticity. Here V is nothing but resultant velocity, when K is the hydraulic coefficient, right? So this is the hydraulic coefficient vector, which is considered for multiplying with the dou V by dou X minus dou U by dou Y. So this vector is measured based on the depth, so depth of the hydraulic analogy. And then resultant velocity is nothing but V is equal to square root of V square plus V square, which is obtained from the X velocity and the Y velocity measurement, right? And then with the help of this equation we could able to find the amount of vortex developed inside the hydraulic analogy, right? And then flow analogy comparison, as well as flow analogy comparison. Since we have no time, I have skipped it, so you may see that particular thing in video module. And then we are going for a hydraulic jump. So for hydraulic jump, it is that flow simulation model just I have given. And then with the help of this model you can have this particular hydraulic jump. So let us play this video. Right, so here we are having the sluice gate. So this is the sluice gate, right, a long duct where all the fluid is passing through this exit, where the depth of the water is flowing from left to right. Now we are using the provision where the surface waves are developed. So all the shallow water is increasing with respect to the wave. This waves is nothing but a slant hydraulic jump. So this is the slant hydraulic jump. So this slant hydraulic jump, it is going to an extent. So up to this extent it is coming up. So this is a sluice gate. So in this sluice gate we are just having the pebbles. So these pebbles are coming out with high velocity, right? The high velocity of pebble is measured with the space and distance, right? All the pebbles are moving from that side to this side with high velocity, c, and then across the wave it is moving with a low velocity where it resembles that oblique shock wave. So flow ahead of oblique shock wave is very high, and then flow behind the oblique shock wave is very less, right? And then here we are maintaining the depth. Now I am increasing the depth, and depth of the column is increasing. Automatically the flow speed is increasing. So this is the complete video which represents the slant hydraulic jump, right? So what are the equations evident for slant hydraulic jump? So there are basically two types of hydraulic jumps, right? One is your normal shock and then oblique shock. First one we are writing for normal shock. So for normal shock, right, it is nothing but right hydraulic jump. So there in the video we have slant hydraulic jump, so it is nothing but oblique shock. So it is nothing but slant hydraulic jump, right? And then you need to measure the velocity. So for this you are measuring the velocity ahead of the oblique shock is measured as g into h1 times h1 plus h2 divided by 2 times of 1 by 2 to the power of 1 by 2, and then h2 by h1. Okay, so this is the velocity equation used for measuring the hydraulic jump velocity, where the fluid particles after hydraulic jump, what about the fluid particles ahead of the slant hydraulic jump, and then behind the slant hydraulic jump, what is the velocity? So ahead of this is u1 is equal to g times. Okay, so behind it is g h, so that is g h2 times of 1 by 2. So this velocity is minimum, so that is u1 is always maintained greater than u2, right? So here you are maintaining the finite height with the help of sluice gate, right? In the video you may see the sluice gate. So with the help of this finite height, sluice gate finite height, okay, so basic velocity of flow is occurred. So basic velocity of flow is nothing but this u2, gs2 power of 1 by 2, right? Not gs2, it is nothing but gh1 power of 1 by 2 is the basic velocity, right? So after framing this, okay, after framing this flow velocity, now you have to put the block on the right hand side of the water flow tunnel. Then the shock waves are going to increase, and then in that oblique shock wave you are just moving the pebbles from left hand side to right hand side, where the velocity of the pebbles is very fast ahead of the wave, and then behind the wave the velocity is slow, where you can measure the value of u2, and then this resembles the oblique shock relations. Okay, that is called as slant hydraulic jump. And then what are the equations considered for this particular model? So the equations considered for oblique shock relations is that you may know very well about oblique shock relations, that is theta beta m relation, and then rho 2 by rho 1 relation, and then p2 by p1 relation, right? So you know all these relations from shock tables, right? But for slant hydraulic jump, what are the equations? So it is nothing but Froude number is equal to 1 by 8 sine square beta, so tan theta 1 minus 2 tan square beta minus 3 tan beta divided by tan theta minus tan beta whole to the power of 1 by 2. So this is the Froude number for first state, and then for the second state, Froude number is equal to h1 by h2 1 divided by sine beta minus theta, and then 1 by 2 times 1 plus h2 by h1, and then what is h2 by h1? That is depth. So 1 by 2 1 plus 8 f for 1 square sine square beta w 1 by 2 minus 1. So these are the relations who are considered for slant hydraulic jump, that is for oblique shock alone, right? For normal shock we will be writing for a different step of equation, and then you should know about these depth measurement devices. So these are the devices: micrometer probe, pressure trapping, and then stereo photography, external plate electrodes, electrical resistance. These two things are followed in electrolytic tank experiments, and these three belongs to any kind of hydraulic analogy as well as Hele-Shaw apparatus, right? These three devices. Then for all steady motion flowing water technique, field measurements. Okay, for steady motion flowing water technique it is there, and then we have soluble dye and photographing method for all pressure measurements, especially in steady or unsteady motion towed model. So what is meant by towed model? So in this towed model, let us explain. I will again explain the concept for towed model kept in a ripple tank. So ripple tank is nothing but, in this tank we are having the water, free surface water is flowing with a speed with respect to oscillating waves. Okay, that is the tank which produces the velocity of water with oscillating medium, that is oscillator. An oscillator is fixed, and then with help of oscillator the tank is operating, right? So let us see the video of towed model. So what is your towed model? Just turning on the small bath, small ripple bath, that is a ripple tank where all the water is flowing from right hand side to left hand side. So you have to check up the velocity of the flow, so that we are keeping the lightweight ball, and then you are confirming that the speed of the flow is 10 centimeter per second. So after that we are keeping the towing model. So this is nothing but towing model. So at the upstream you are just bringing out the towing model. So it is nothing but a cylindrical model. So in this cylindrical model, behind the cylinder we have the vortices. So what type of vortices it is? It is one common vortex street, and then the model is slightly oscillated in the upstream condition, and again in the downstream, again you are keeping the model in the downstream, and you are visualizing the effect with high amount of oscillation, right? A high amount of oscillation is produced on the downstream, right? Why this high amount of oscillation is created in the downstream? Because when the waves are accelerated from initial position, the waves are shallow water is very minimum, but the frequency of water tends to increase due to the incompressibility of water and viscosity of water. It randomly increases and it creates oscillation at the downstream path. So this is one towed model technique which I am showing here, and then at last you are going to place it in the fast stream. So this is the fast stream condition. So after this we have a steady level of flow where all the vortex streets are formed behind it, right? So this is nothing but one karma vortex street. So the vortex will be circulating, and this vortex is not stationary and it is moving along with the stream. So that is called as vortex streets, right? And then these are the thing used for producing the oscillation in a shallow water. And then limitations. What are the limitations? So first limitation is two-dimensionality. And then specific heat ratio, and then velocity of wave propagation, next vertical acceleration, viscosity and heat conductivity, surface tension, and then appropriate techniques, right? So these are the limitations of hydraulic analogy. So two-dimensionality, specific heat ratio, velocity of wave propagation. So two-dimensionality is that it is applicable only for two-dimensional flows. That is the main greater disadvantage. And then specific heat ratio, we have talked about that we are maintaining gamma is equal to 2 for any kind of hydraulic analogy, but for any gas flow it is up to 1 to 1.67 for different gases and mediums. And then velocity of wave propagation, and here is also velocity is also affecting. So which velocity is affecting? So here we are neglecting the velocity of u and the v, and then w is the third velocity, that is your z velocity. Your z velocity in hydraulic analogy is considered, is always considered, because this z velocity is moving from left hand side to right hand side along the shallow water, but you are neglecting that. But this z velocity is also important for considering the three-dimensional case. And then vertical acceleration. So for any kind of oblique shocks, vertical velocity is important, right? But for upstream and downstream case, you are considering for forward and rearward velocities as v1 and v2, and you are not considering for vy1 and vy2. But this vy1 and vy2 is very important for vertical case problems. And then viscosity. So since water is having a high viscous, right? And then very good conductor of heat conductivity. Water is a substance of highly viscous and heat conductivity. There is some problem arises when the normal shock waves or oblique shock waves is simulated on a live running tunnel. So in a live model, we are not considering that viscosity and heat conductivity, just we are running the shallow water hydraulic analogy directly, right? So for normal shock and oblique shock, heat conductivity is more, where viscosity is less. And then surface tension. So surface tension, you know very well about the surface tension of the shallow water. If we have any disturbances on the upper free surface, right? We have the readings, deviation of readings, right? Due to surface tension. And then appropriate techniques. So we are using some appropriate techniques for building any type of physical domain, right? For any physical domain, right? You could able to construct any kind of physical domain. So based on the physical domain construction, we may use some appropriate technique. Okay, so these appropriate technique will lead to the limitations, such as measurement of all these 5 or 6 different properties. This may not be said to be accurate, right? So it is still accuracy, but it is nominal accuracy. All the results of hydraulic analogy gives nominal accuracy, not with a high accuracy, right? Next session we will going to discuss about flow visualization techniques, that is intrusive and non-intrusive method, especially Schlieren system, interferometer, and then shadowgraph technique. Okay, we will see in next class. So students who are all having any doubts regarding this session, you may ask it or post it in comment box, or else you may contact me individually, or else you may come on with other new sessions, right? I will come up on with other sessions like flow visualization techniques as well as the other methods which is carried out inside the tunnel. Okay, thank you.